Let's talk about rate of change. We will use what we learned so far about the concept of differentiation relating to tangent lines. This definition may be starting to crystallize in your mind, but let's examine this concept in another context just to be thorough. By examining movement, distance over time, or velocity. Welcome to Learn with Red. I'm Red and I make learning videos like this. Click like or subscribe to see more and get notified when I upload new videos. And oh, it's time right now to Learn with Red. When we introduced calculus, we talked how Newton pondered a falling body, perhaps like this mythical apple. He observed that if the apple was dropped some short distance from rest, meaning with an initial velocity vi equals 0, that velocity would increase in the negative direction, downwards, every single instant until it hits the ground. He then wondered, how can I calculate the velocity at any particular instant during its fall? Newton called this instantaneous velocity. Some years before this, Galileo had already discovered that distance traveled s of t by a falling object is a function of time. S of t equals 4.9 t squared. Why the symbol s for distance? Just know that in ancient times, scholars used Latin and the Latin word for distance is spatium or space, hence s. So s of t is distance traveled and s of t means s as a function of t, time, just like f of x or g of x. So Galileo defined s of t, distance as a function of time, equals 4.9 square of time or 4.9 t squared. So Galileo can calculate how many meters the apple would fall given some time t in seconds. But Newton wanted to calculate not the distance traveled at an interval of time. Remember, what did Newton want to compute? Newton wanted to compute for the velocity at any instant of time. What is the velocity of the apple at a particular moment in time? For example, what is the velocity of the apple at t equals 5 seconds of its fall? Let's see how Newton did it. Just like we did in lesson 2 with the secant and tangent lines, let's make an approximation. We can calculate average velocity as v average as distance traveled over time elapsed in meters per second, m for the distance traveled and second or s for time elapsed. Just a review in physics. Why velocity? Why not speed? Direction. The movement of the falling apple with the dimension of space in meters per second or time elapsed has a direction downwards. And using Galileo's equation, we can express distance traveled as the difference between 2 points. Say, distance traveled in 5 seconds or s of 5 and in 6 seconds, s of 6. If we subtract s of 6 minus s of 5, we are necessarily describing the distance traveled during the period from t equals 5 to t equals 6 seconds after being dropped. That will also mean that the time elapsed is 1 second. Follow me. One 176.4 minus 122.5 divided by 1, that is equal to 53.9 meters per second. Let me ask you, what is this number 53.9 meters per second? This number is the average velocity from t equals 5 to t equals 6. But what exactly is Newton after? He's after what is the precise velocity of the apple at the exact moment t equals 5 seconds of its fall. We can do something similar to the second line in lesson 2 and nudge the point at t equals 6 closer and closer to the point at t equals 5. Let's execute this using Excel. Using Excel, let us see how the curve s of t equals 4.9t squared looks like. Starting with t equals 0, s of t equals 4.9 times 0 squared, or 0. Then we compute for s of t, or distance traveled, for t equals 1, 2, 3, 4, 5, and 6. Copying the formula, we get the distance traveled from t equals 0 to t equals 6 seconds. Now let's plot the line graph with t in the x-axis and the s of t in the y-axis, and we get this curve of distance traveled with respect to t. The apple begins at the top at t equals 0 and an initial velocity of 0. Then it falls to t equals 1, t equals 2, t equals 3, t equals 4, t equals 5, and t equals 6 when it hits the ground. Well, it looks a bit confusing seeing the apple falling down and the curve going up. This is because we're plotting distance traveled. Let's do something different. Let's plot the position or elevation instead of distance. We know that the distance traveled in 6 seconds is 176.4 meters. Let's put the apple at the position or elevation 176.4. Then at t equals 1, position is at 176.4 minus s of 1. At t equals 2, position is at 176.4 minus s of 2, and so forth. Now we can compute for the exact velocity at precisely t equals 5 seconds of its fall. Using the second line we learned in lesson 2, we draw a line connecting the points at t equals 4 to t equals 5 seconds. S of t equals 176.4 minus 4.9 times the square of 4. That's elevation 98. And we know the position at t equals 5 seconds is at elevation 53.9. And 98 minus 53.9 equals 44.1. 53.9 minus 53.9 equals 0. Time elapsed from 4 to 5 is negative 1 second. Finally, 44.1 meters over negative 1 equals negative 44.1 meters per second. That's the average velocity from t equals 4 to t equals 5 seconds. That's the rise over run negative velocity, meaning downwards. Now, we nudge the point closer to t equals 5 at t equals 4.5 seconds. The second line becomes steeper. 176.4 minus 4.9 times 4.5 squared equals 77.2 minus 53.9 equals 23.28 divided by negative 0.5 equals negative 46.55 meters per second. That's a faster average velocity to t equals 5, negative meaning downwards. Now, we nudge the point closer still at t equals 4.9 seconds. The apple falls to elevation 58.8 and only 4.85 meters close to t equals 5. Divided by negative 0.1 equals a velocity of negative 48.51 meters per second, faster and downwards. Finally, we nudge the point still closer at t equals 4.99999 because t equals 5 minus t equals 5 is dividing by 0, which result is undefined. So we can state that at the limit of infinity, the velocity at t equals 5 equals 49 meters per second, negative meaning downwards. That's the slope of the tangent line of the curve at point t equals 5. Also, that is how Newton introduced calculus for computing the instantaneous velocity at a precise moment of time of a falling body. For the next lesson, Let's continue examining introductory calculus concepts. But before that, let's have learning assessment.